A warm welcome to you all for another class on quantum mechanics. In this session, we will discuss about Planck hypothesis, photoelectric effect, de Broglie concept of dual nature of matter or de Broglie wavelength, then Compton effect, and Davisson Germer experiment. First, we discuss about Planck hypothesis. The previous class we already discussed about the Planck hypothesis or Planck's radiation formula. During that time we already mentioned the Planck hypothesis. A fundamental law of quantum theory stating that energy associated with electromagnetic radiation is emitted or absorbed in discrete amount which are proportional to frequency of radiation. That is, energy radiated or absorbed in discrete unit of energy called quanta, that is E is equal to h nu. And Planck assumed that atoms of the walls of the black body behaves like a tiny electromagnetic oscillator. We already mentioned while discussing the black body radiation. The walls of the black body behaves like a tiny electromagnetic oscillator, and each oscillator can oscillate its own characteristic frequency. We already discussed. Each oscillator can oscillate its own characteristic frequency, and the oscillators emit electromagnetic energy into the cavity or absorb electromagnetic energy from it. This emission and absorption takes place only in discrete unit which is called quanta. So the Planck hypothesis is oscillators having energy En is equal to nh nu, and the oscillators can absorb or emit energy only in discrete unit that is called quanta. That is delta En is equal to delta of nh nu. For example, delta of nh nu for n is equal to minus n is equal to 1. So what we get is h nu. So oscillators can absorb or emit energy in discrete unit called quanta. These are the two Planck hypotheses. Based on this hypothesis, we derived the Planck's radiation formula. We already discussed in the previous class. Next, we will discuss about the particle nature of radiation. See, particle nature of radiation or particle nature of light. So, up to that time, the concept about light is it's a wave. It's a wave. I think you may recall the concept of light during Newtonian time. Newton argued that light is a particle. I think you may heard about the corpuscular nature of light. Okay, and at that time, some of the physical phenomena could not be explained with this particle theory or corpuscular theory of light. The phenomena are interference, diffraction, etc. These type of phenomena could not be explained with this particle theory or corpuscular theory of Newton's theory of light. And the concept about the light or corpuscular theory of light was modified by Huygens wave theory, and you may heard about Young's double slit experiment. Anyway, it is not part of our syllabus. So today we will discuss about the particle nature of radiation. In 1887, Heinrich Hertz he discovered the photoelectric effect. The photoelectric effect is not discovered by Albert Einstein. Albert Einstein gave satisfactory explanation on photoelectric effect, and he discovered Nobel Prize. And he secured Nobel Prize, not discovered. He secured a Nobel Prize. Hertz discovered the photoelectric effect, and the wave theory of light could not explain this photoelectric effect. Okay, Albert Einstein gave satisfactory explanation for photoelectric effect, and he got Nobel Prize for that. And this Heinrich Hertz discovered the photoelectric effect, and he could not explain this photoelectric effect based on this wave theory. And this photoelectric effect, what is actually within this photoelectric effect is that electrons were emitted only if the frequency of radiation was above some certain critical value. All the frequency cannot emit radiation from the, or not air radiation, cannot emit electrons from the metal surface. Electrons were emitted only if the incident light is having frequency is much higher than some critical value. Okay. Then second inference is, or second observation from this photoelectric effect is that maximum kinetic energy of the electron, maximum kinetic energy of the ejected electron, we can say ejected electrons. Suppose there is a metal surface, the maximum kinetic energy of the electron emitted from this metal surface is not depends upon the intensity of the incident radiation. Okay, not depends upon the intensity of the incident radiation, but depends upon the frequency of the incident radiation. See, what is the difference between energy and intensity? Intensity means the number of photons. Okay, energy is related to its frequency. So the kinetic energy of the ejected electron depends only on the frequency. Okay, it is not, does not depend upon the intensity of radiation. So the maximum kinetic energy of the ejected electrons from the metal surface depends only on the frequency, not on the intensity. Okay, then greater the intensity leads to large number of electrons. For example, there is a one photon is having frequency is much higher than the critical value. Suppose there is a light is coming on a metallic surface. Okay, actually, what is photoelectric effect? Photoelectric effect is the ejection of electrons from the metal surface when a light of suitable frequency falls on it. Suitable frequency falls on it. Suppose there is a light which is having frequency is higher than the critical value. Then suppose the one photon is coming, then one electron is ejected. If two electrons are coming, then two electrons are emitted. Three photons are coming, then three electrons are emitted. Then five photons are coming, five electrons are emitted. Okay, so which means that greater the intensity means the number of electrons also increases. Okay, these are the observations of photoelectric effect, but Henry Hertz could not explain this photoelectric effect. Okay, so in this situation, Albert Einstein argued that light consists of quanta of energy h nu. Light consists of quanta of energy h nu. That the emission of photoelectrons was the result of interaction of single quantum with the electron. See, he argued that the emission of electron is due to the interaction of single photon with electron. Okay, so one photon is coming, a packet of energy which is called h nu. This h nu is interacting with the electron and this electron is ejected. Okay, if two photons are coming, it interacts with two electrons and two electrons are ejected. Okay, so this is the Einstein's argument, and based on this, in 1905, Albert Einstein wrote, monochromatic radiation behaves as if it consists of mutually independent energy quanta of magnitude h nu. So that's actually he wrote in that research paper. Okay, so before explaining photoelectric effect, what are the I will just mention what are the classical expectation. These are the classical. See, this one is the classical expectation, but that is not the correct one. Okay, this is the classical expectation, but it is not observed. Okay, so this is the photoelectric effect apparatus. There's a metal plate. See, light of frequencies falls on this one. Electrons are ejected from this metal plate. There's a collecting plate. So electrons are attracted towards this collecting plate, and there's a possibility of current flow through this ammeter. Then current can be recorded. Okay, this supply is for giving proper biasing or potential difference. Okay, so electrons are emitted. If we give some positive potential here, then what happens? Electrons are attracted towards this collecting plate, and there is a possibility of current flow. Okay, this is what actually the systematic diagram of photoelectric effect apparatus. Then we are moving to the classical expectations. What are the classical expectations? See, electric field E of light exerts force F is equal to minus E into E. Okay, we know that light, which is having light is nothing other than electromagnetic field or electromagnetic wave. So, an electromagnetic wave has both electric and magnetic field, which are mutually perpendicular. Because this is suppose this is a plane polarized one, and this is an electric field, and this is a magnetic field, and it is moving in this direction. Suppose this is in x direction, this is y direction, it is moving in the z direction, mutually perpendicular. Okay, so anyway, light consists of an electric field. Then the force exerted on this charge. So light is coming and there is an electron there. So light is coming. The electric field within this light interact with this electron and there is a force. That force is called Coulomb force. What is Coulomb force? If is equal to 1 by 4 pi epsilon 0 q1 q2 divided by r square. I think you may heard about that during your plus 2 time. Okay, anyway, F is equal to this one, or in another words we can say F is equal to minus E into capital E, where E is the electric field and minus E is the charge. Okay, E is the charge, minus sign represents the charge of an electron. As the intensity increases, force increases, so the kinetic energy of the ejected electron should increase. That is a classical expectation. See, intensity increases means electric field increases, which means force increases. Since the force increases means kinetic energy of the ejected electrons should increase. That is a classical expectation, but it is not actually happened. Okay, so there is one classical expectation which is not happened in photoelectric effect. Another one is electron should emit whatever the frequency of the light, because electric field is large, so even if the frequency is very small, there is a possibility of ejection of electron. That is another classical expectation and which is not happened in real photoelectric effect. Okay, and another one is very low intensities expected time lag between incident photon and ejected electron. That is not that is also not happened. Okay, these are the classical expectations, but that is not observed in photoelectric effect. Okay, what observed is just opposite, just it's contradictory to this classical expectation. That's why Henry Church could not explain this photoelectric effect. Okay, so that's about the classical expectation. Now we are moving to the actual the definition of photoelectric effect. Photoelectric effect states that when an electromagnetic radiations of sufficiently high frequencies incident on a certain metal surface, electrons are emitted from the surface. Okay, so in light of sufficiently high frequency mark falls on the metal surface, electrons are emitted. This is what we call photoelectric effect. Okay, now we can see this one is a potassium metal and it has a work function of 2 electron volt. Just see, just look at this figure. Suppose this is a potassium metal surface and it has a work function of, I will tell you what do you mean by work function. Okay, anyway, work function is 2 electron volt, which means that 2 electron volt is needed to eject the electrons from the potassium. Okay, this is suppose this is a potassium metal and 2 electron volt is its work function, which means that 2 electron volt is needed to eject electrons from the metal surface. Okay, now based on this figure, I would like to tell you what happens when blue light incident on this metal surface, what happens when green light incident on this metal surface, and what happens when red light is incident on this metal surface. Okay, blue light, which means that it has a wavelength of 400 nanometer, and green light, which has a wavelength of 550 nanometer, and red light, which has a wavelength of 700 nanometer. And each wave has, since the wavelength is known, so we can calculate the energy of the incident radiation, which means that the energy of the blue radiation or blue light, energy of the green light, energy of the red light. By using the formula E is equal to h nu. H we know, nu is equal to c by lambda. C is the velocity light and lambda is the wavelength. For blue light, lambda is equal to 400 nanometer. Green is 550 nanometer and red is 700 nanometer. So we can calculate or we can find the energy of each light. For blue light it is 3.1 electron volt, see, and green light it is 2.25 electron volt, and red light which is 1.77 electron volt. Okay, see the potassium metal surface. The minimum energy required to eject the electron from the metal surface is 2 electron volt. So see, in this blue light, what happens to in the case of blue light? It has an energy of 3.1 electron volt. See, it has an energy of 3.1 electron volt, which is well above 2 electron volt. Potassium has an energy of 3.1 electron volt, which is well above 2 electron volt. Okay, so there is an ejection of electrons on the potassium metal surface. Okay, now coming to the green light, which has an energy of 2.25 electron volt, which means it is well above 2 electron volt. So there is an ejection of electron from the metal surface. Then coming to the red light, which has an energy of 1.77 electron volt. Do you know how this 1.77 came? Nothing other than h nu or hc by lambda. This h nu is equal to hc by lambda. From using that relation, we can calculate the energy of a single red photon, which is equal to 1.77 electron volt. 1.77 electron volt, it is well below the work function, 2 electron volt. So there is no electrons ejected when red light falls on this metal surface. Okay, is it clear? So from this figure, we can say a dim blue light. Dim blue light means intensity is very low. Okay, for example, suppose a blue light of 1 photon can eject 1 electron from the potassium metal surface. But in the case of red light, suppose there are 1000 or 1 lakh red light is false. Suppose 1 lakh red light is false on the potassium metal surface. There is no single electron ejected from the metal surface. Okay, so a dim blue light can eject electrons from the metal surface, but a bright or suppose the intensity is very high or very high intensity red light cannot eject electrons from the metal surface because its energy is low, even though the intensity is large. Even if the intensity is large, the energy is very low, so electrons could not ejected from this metal surface. Okay, I think it is very clear. Now we are moving to the Einstein's photoelectric equation. See, there's a light is falls on the metal surface. There is an ejection of electrons on the metal surface. A photon with an energy h nu, see, strikes an electron and ejects it from the metal. Okay, so light of energy h nu falls on the metal surface and electrons ejected. The light of energy h nu falls on the metal surface is that energy is used for two purposes. The one is the ejection of electrons from the metal surface, that is called the work function. It is a part of energy is used to eject electrons from the metal surface. Okay, the remaining energy is the kinetic energy of the ejected electron. Clear? So h nu is the incident photon energy, Ke is the kinetic energy of the ejected electrons, and W is the work function, that is work to remove electrons from the metal surface, and it is always denoted by phi, or it is termed as work function. Okay, so from this equation we can calculate, or we can write, kinetic energy of the ejected electrons is equal to h nu minus work function, or h nu minus phi, or simple words we can say kinetic energy is equal to h into nu minus nu 0. Okay, so Einstein's quantum theory of light states that electromagnetic radiations travel as a tiny packet of energy called quanta or photon and behaves like a particle. See, and this was published in his famous 1905 paper on a heuristic point of view about the creation and conversion of light. The title of the research paper is this. Okay, actually, what is the real outcome, or what is actually the photoelectric effect? Photoelectric effect, in simple words, we can say it demonstrates the particle nature of wave. Photoelectric effect demonstrate the particle nature of wave, because the incident one is a light or photon, that is a incident one is a light which is a wave, and what we are getting is an electron, that is a particle. So photoelectric effect demonstrate the particle nature of wave. I think it is clear. So that's about the photoelectric effect, and Einstein gave satisfactory explanation for this photoelectric effect. His explanations are only those photons which can supply energy more than work function can liberate electrons from the metal. Okay, so incident photon must possess a minimum energy, or there should be a minimum frequency. That frequency is called threshold frequency. Okay, so photons, the incident photon, the electrons can eject only when the incident photon is having energy much higher than the work function. Okay, that minimum energy or that minimum frequency is called threshold frequency. And second point is the kinetic energy of the ejected electrons depends only on the incident frequency, not on the intensity. If we increase the frequency means the kinetic energy of the ejected electron increases. Okay, the first one is there should be a minimum frequency, that is called threshold frequency. In simple words, there should be a threshold frequency. Incident light should have a threshold frequency. Second one is the kinetic energy of the ejected electron depends only on the incident frequency, not on the intensity. Okay, if you increase the intensity means, sorry, if you increase the energy or frequency means the kinetic energy of the ejected electrons increases. Okay, then third one is if you increase the intensity, which means the large number of electrons ejected. I already mentioned. Suppose there is a one photon incident on the metal surface, there is one electron ejected. If we allow to fall 10 photon, which means that there is an ejection of 10 electrons. Okay, then the fourth one is there is no time lag between incident photon and ejected electron. That is for Einstein's explanation of photoelectric effect. Okay, now we are moving to the stopping potential. The stopping potential refers to the voltage difference required to stop the electron from moving between plates and creating a current in the photoelectric experiment. Okay, see, stopping potential or stopping voltage refers to the voltage difference required to stop the electrons. Okay, suppose look at this figure. When light or photon stream which falls on this metal surface, electrons are ejected. Okay, then these ejected electrons are collected using this electrode, and it falls through this ammeter. Then there is a current. Okay, there is a current. If we increase the intensity, which means that suppose there is a one photon, then one electron, suppose we can call this one as one current. If there are 3 or 5 photon, the current ampere is 5, for example. Then there is a 10, the current is 10. So that's why we denote as I1, I2 and I3. If we increase the intensity means the number of electrons increases, which means current increases. Okay, the stopping potential is the potential required to stop the flow of electrons. Stop the flow of electrons. Suppose now it is a positive potential. Suppose it is a positive potential. Electrons are attracted towards this plate and there is a current. Okay, now I just reduce the positive potential here and reduces. This is the, see, this axis is x-axis is the voltage. If we reduce the voltage, what happens is, see, if you reduce the voltage, and what happens is it becomes negative. This plate becomes negative, which means that there is no electrons falls on this collecting plate, which means that the current stops. Okay, normal case there is a flow of current, and if we reduces the voltage here, suppose it is positive voltage, there is a current, then positive voltage reduces to, suppose if you are giving plus 3 voltage, there is current, then I reduces to plus 2, there is little current, plus 1, again there is current, then 0, again there is current, then minus 1, minus 2, minus 3. What happens is there is no current flows. Okay, there is no current flows. So the stopping potential is the voltage difference required to stop the electrons moving between the plates and creating a current in the photoelectric sphere. This is what we call photoelectric. So for stopping potential in photoelectric. I think it is clear. Next, I would like to discuss about the Compton effect. The theory behind the Compton effect was also to prove that light has a particle nature. Also, see, I already mentioned that the photoelectric effect demonstrates the particle nature of light. The Compton effect also demonstrates the particle nature of light. And the Compton effect provided a clear-cut example of a process in which quantum radiation carrying energy as well as momentum. Listen, Compton effect provides a clear-cut example of a process in which quantum of radiations carrying energy as well as momentum. Okay, which means that this photon is having energy h nu, which also possesses momentum, or which possesses momentum also. Okay, and this for Compton effect demonstrate the quantization of momentum. Compton effect demonstrate the quantization of momentum. I would like to repeat, for Compton effect, which proves the particle nature of light, and he argued that the light h nu, which is having energy as well as momentum, and it demonstrates the quantization of momentum. Okay, so in this Compton effect, you can find there's an incident photon, there's a target electron which is at rest. Incident photon strikes, or the incoming photon or incident photon which collide or scattered by this electron. After scattering, this electron gets an energy from the incident photon and remaining photon scattered off with an angle theta. See, this is an incident photon having energy nu or h nu and frequency nu, and since it is an incident photon, we call this one as lambda I, incident wavelength lambda I. This is a target electron which is at rest. After scattering, this electron gains some energy and it moves with an angle phi to this original photon direction, and it carries some energy that is called recoil of electron. Since a part of the incident photon energy is used for the recoil of electron, the remaining energy is scattered off with an angle theta to the incident photon direction, and this final wavelength we denote this one as lambda f. And Arthur Compton, he derived a formula for difference between this lambda f and lambda I. Okay, so lambda f minus lambda by I, which means that final photon wavelength minus incident photon wavelength, which is equal to delta lambda, that is called delta lambda, that is called Compton shift delta lambda, which is equal to h by m0 c into 1 minus cos theta, that we will derive. Lambda f minus lambda I, which is equal to delta lambda, that is equal to h by m0 c into 1 minus cos theta. See, incident photon having energy h nu, its frequency is nu, wavelength is lambda I. After scattering, a part of energy is used for recoil of electron. Remaining energy means the energy is somewhat less than the incident photon energy. The scattered photon energy is less than the incident photon energy. That is very clear. Okay, incident photon energy, a part of this incident photon energy is used for recoil of electron. Remaining energy is scattered. So this photon energy or scattered photon energy is less than incident photon energy. The scattered photon frequency is less than incident photon frequency. Okay, then scattered photon wavelength is greater than incident photon wavelength because frequency and wavelength are reversed. Okay, so scattered photon wavelength is higher than incident photon wavelength, not in terms of frequency. Scattered photon frequency is less than incident photon. Scattered photon frequency is less than incident photon frequency. Now coming to the wavelength, scattered photon wavelength is greater than incident photon wavelength because frequency and wavelength are just opposite, inversely proportional. Okay, so in 1923, Arthur Compton investigated the scattering of X-rays by a block of paraffin film and found that the wavelength of the radiation scattered at an angle 90 degree is greater than the wavelength of incident radiation. Okay, that we will discuss or derive. And this Compton effect, the collision between photon and electron, Compton effect, collision between photon and electron. Actually, the Compton effect is between photon and electron. That is, inside in the photon, there is an electron, target electron. When a photon strikes an electron and is scattered away from its original direction, see, when photon strikes an electron and scattered away from the original direction, see, this is the original direction. I think you can see the movement of this cursor. This is the original photon direction. See, scattered off from the original photon direction, which means that electron scattered off by an angle phi and this photon scattered off by an angle theta. So when photon strikes an electron and is scattered away from its original direction of motion, while the electron receives an impulse and begin to move. Okay, so we can say loss in photon energy is equal to gain in electron energy. Loss in photon energy, incident photon energy loss. Okay, and that loss is gain in electron energy or recoil energy. So now we are moving to the derivation of this photoelectric, the Compton effect. Now consider the elastic collision. See, elastic collision means both energy and momentum conserved. Momentum is conserved in both elastic and inelastic collisions. Okay, elastic collision, energy and momentum conserved. More specifically, kinetic energy and momentum conserved. Okay, in inelastic collision means here inelastic collision also momentum conserved. In inelastic collision, its kinetic energy is not conserved. So total energy is conserved. What will be the reaction? Total energy is conserved, but in elastic collision, energy and momentum are conserved. In inelastic collision, momentum is conserved, only the kinetic energy is conserved. Okay, in inelastic collision, there is a possibility of another form of energy. There may be a sound energy, there may be a heat energy, some mechanical energy may be there. Okay, so consider elastic collision, energy as well as momentum are conserved. Now we look at the momentum of incident photon. The moment of incident photon can be represented as h nu by c, because we know E is equal to h nu and E is equal to mc square. You can write in a paper E is equal to h nu and E is equal to mc square. We can say mc square is equal to h nu. So mc is equal to h nu by c. So mass and velocity, that is momentum. So initial photon momentum is equal to h nu by c. And similarly, scattered photon momentum we can say h nu prime by c. Okay, so initial photon momentum is h nu by c and scattered photon momentum is h nu prime by c. Okay, and initial and final electron momentums are zero, because initially the electrons are at rest in this frame of reference. Suppose the frame of reference is associated with the electron. So initially the electrons are at rest and its momentum is zero. After scattering, after collision, its momentum is denoted as p. Now coming to the momentum conservation, initial momentum is equal to final momentum. Okay, now look at the initial momentum in the case of original photon direction. Now consider the momentum conservation in the photon direction, incident photon direction. I think you can see the movement of this cursor. This is the incident photon direction. In this photon direction, before collision momentum is equal to h nu by c plus 0. So h nu by c plus 0. After that, its momentum is, this is h nu prime by c, but its direction is not in this incident photon direction. Its direction is theta with this incident photon direction. Okay, since we are dealing with the horizontal direction or x-axis. This can be treated as or the component of the photon in this direction. Please listen. The momentum component of this scattered photon in x direction or horizontal direction or incident photon direction. The component of this scattered photon momentum in incident photon direction is cos theta time. Okay, in y direction it is sin theta time. In trigonometry, you may heard about that. Okay, so in this incident photon direction, its scattered photon momentum is equal to h nu prime by c into cos theta. Okay, similarly for electron, its momentum is equal to p cos phi. Phi is the angle here and theta is the angle here. So this recoil photon momentum in incident photon direction, recoil electron momentum in incident photon direction is equal to p cos phi. Okay, so in the original photon direction, consider the momentum conservation. Before collision momentum is equal to after collision momentum. Before collision momentum h nu by c plus 0, which is equal to scattered photon momentum in this direction, incident photon direction, that is equal to h nu prime by c into cos theta, and for electron is equal to p cos phi. Okay, now coming to the momentum conservation perpendicular to the incident photon direction. See, perpendicular means you can see the cursor movement perpendicular to the incident photon direction. So in this direction, the incident photon momentum is 0, the electron momentum is also 0. So we can write 0 plus 0, that is 0. Okay, then scattered photon momentum, that is h nu prime by c. Now we are considering the momentum perpendicular to the incident photon direction, not the incident photon direction, perpendicular to the incident photon direction. So there is a sine theta or sine component. So h nu prime by c sine theta minus again p cos. The minus sign comes because of, you may heard about sine 90 minus theta, cos 90 minus theta. So the trigonometric relation. So in the perpendicular direction we have h nu prime by c sin theta minus p sin phi. 0 is equal to h nu prime by c sin theta minus p sin phi. Okay, now you can see this equation. You can multiply c throughout this equation. This equation and this equation also. You can multiply. I think you can take a paper and write this equation and multiply c throughout this equation, these two equations. Then we will get equation like this. Pc cos phi is equal to h nu minus h nu prime cos theta. And Pc sin phi is equal to h nu prime sin theta. It's clear? Pc cos phi is equal to h nu minus h nu prime cos theta. Pc sin phi is equal to h nu prime sin theta. Then you can square this equation and also this equation and then add. You can square and add this equation. If we square, the left hand side is p square c square cos square phi. Okay, then you can expand this one, and this equation left hand side is p square c square sin square phi. If we add, what happens? P square c square cos square phi plus p square c square sin square phi. So p square c square we can take outside. So what we get is p square c square into cos square phi plus sin square phi. So please listen. P square c square taken outside. So cos square phi plus sin square phi. You can write a paper and square these two equations and then add. Then cos square phi plus sin square phi, that is 1. So what we get is p square c square is equal to h nu the whole square minus 2 h nu prime cos theta plus h nu prime the whole square. Okay, because p square c square cos square phi is equal to this is just like an a minus b the whole square, that is a square minus 2ab, okay, plus b square is h nu prime the whole square cos square theta. Here also h nu prime square sin square theta. Okay, h nu prime the whole square we can take outside. So what we get is sin square theta plus cos square theta, that is again 1. So what we get is p square c square is equal to h nu the all square minus 2 h nu prime cos theta plus h nu prime the all square. Okay, this is one equation. You can number this equation as number 1, equation number 1, just like. Okay, and keep this equation. We will use this equation after deriving another one. See, if m is the rest mass of an electron and its initial energy is mc square, then relativistic expression for the energy capital E is equal to square root of m square c square, sorry, m square c raised to 4 plus p square c square. So relativistic expression for the energy of an electron. Suppose E is the electron and its m is the mass, then relativistic expression for the energy E is equal to square root of m square c raised to 4 plus p square c square. E is equal to m square c raised to 4 plus p square c square. And we know that the total energy is equal to kinetic energy plus mc square. Okay, then instead of this E, I think you can see the cursor movement. Instead of this E, we can use kinetic energy plus mc square. Okay, and square this equation, this yellow box equation, square this equation. What happens is E square, which is kinetic energy plus mc square, the all square. Okay, that is written here. Then m square c raised to 4 plus p square c square. Okay, it's clear. Now if we expand this equation, what happens is, see, kinetic energy square plus, that is a plus b the whole square, kinetic energy square plus 2 times kinetic energy into mc square plus m square c raised to 4. Okay, and this m square and c raised to 4 and m square and c raised to 4, this will get cancelled. So what we get is p square c square is equal to kinetic energy square plus 2 m c square kinetic energy. And we know that the kinetic energy of the ejector electron, as per Albert Einstein's photoelectric equation, kinetic energy of the ejector electron is equal to h nu minus h nu prime. The gain in kinetic energy is equal to, or kinetic energy is equal to h nu minus h nu prime. Then we can substitute the value here, h nu minus h nu prime, the all square, plus 2 mc square into h nu minus h nu prime. Okay, so see, look at this equation. Left hand side is p square c square is equal to h nu minus h nu prime the all square plus 2 mc square into h nu minus h nu prime. Once again I would like to repeat, this is p square c square. So in the previous case we came across this equation, p square c square is equal to h nu the all square minus 2 h nu prime cos theta plus h nu prime the all square. Now come look at these two equations. The left hand sides are same, so right hand side must be same. So we can write h nu the all square minus 2 h nu prime cos theta plus h nu prime the all square, which is equal to this one. What is h nu minus h nu prime the all square plus 2 mc square into h nu minus h nu prime. Okay, so see this equation, h nu the all square minus 2 h nu prime cos theta plus h nu prime the all square, that is written here. And right hand side, kinetic energy, that is h nu the all square plus 2, sorry, h nu prime the all square minus 2 h nu prime, that is kinetic energy square, plus 2 mc square into then kinetic energy h nu minus h nu prime. Okay, see, look at this equation. See, this h nu the all square, right hand side also h nu the all square, that get cancelled. Here h nu prime the all square, here also h nu prime the all square, that's also get cancelled. See, these two terms get cancelled. Then see, there is 2 also in this the common factor is 2 is also there, so we can remove that also. So what happens is mc square into h nu minus h nu prime, that is h nu prime into 1 minus cos theta. You just take a paper and derive this one. We will get. Okay, here one h nu minus h nu prime is there. Here h nu minus h nu prime is here. Here also h nu prime cos theta. So in this situation we can take h nu prime outside. So what we get is 1 minus cos theta. Anyway, we will get this equation. mc square into h nu minus h nu prime, which is equal to h nu prime 1 minus cos theta. What we get. You can also derive this equation. Then see, nu is equal to c by lambda. Okay, nu is equal to c by lambda. Here also c by lambda into c by lambda, c square by lambda square you will get. Sorry, c square by lambda prime, not lambda square. See, look at this equation. Here there is mc square. Here suppose it is nu is equal to c by lambda, nu prime is equal to c by lambda prime. So there is c into c, that is c square. This c square and this c square get cancelled. Okay, and here there is c by lambda, here there is c by lambda prime. So we can take one c outside. So that what we get is mc. Here one h can be taken outside. Here there is 2h or h square. So one h get cancelled from this h and this h, and there is one h that goes here. So mc by h into 1 by lambda minus 1 by lambda prime, which is equal to 1 minus cos theta into divided by lambda prime. Okay, then this h goes to this place and mc goes to this place. So what we get is 1 by lambda minus 1 by lambda prime is equal to h by mc into 1 minus cos theta divided by lambda prime. Then you can take the LCM. LCM is lambda prime. So what we get is lambda prime minus lambda divided by lambda prime is equal to 1 minus cos theta divided by lambda prime. See, mc by h into lambda prime minus lambda divided by lambda prime as per LCM, that is equal to 1 minus cos theta divided by lambda prime. Here also denominator lambda prime, here also lambda prime, that get cancelled. So what we get is lambda prime minus lambda is equal to h by mc into 1 minus cos theta. So that is what the Compton shift. Lambda prime or lambda f. Lambda prime means final wavelength. Okay, lambda is initial wavelength, that is h by mc into 1 minus cos theta. This lambda prime minus lambda is called the change in wavelength, which is called Compton shift. And this h by mc is also it is also known as the Compton wavelength. H by mc is Compton wavelength. So in simple words we can say delta lambda is equal to lambda c into 1 minus cos theta, where lambda c is the Compton wavelength, that is h by mc. So Compton effect shows that electromagnetic radiation exhibits particle behavior when interacting with electron, obeying the conservation laws of energy and momentum. Compton effect shows that electromagnetic radiations exhibit particle behavior when interacting with the electrons, obeying law of conservation of energy and momentum. That's about the Compton effect. Next we will discuss about the wave nature of matter and de Broglie hypothesis. As everyone knows, this de Broglie hypothesis is radiation possess dual character. Both, or we can say matter can have both wave nature and particle nature. Okay, see, before the observation of photoelectric effect and the Compton effect, the concept about light is nothing other than wave, because it supports the interference and diffraction, those type of phenomena. Okay, so interference and diffraction can be explained with this wave theory of light, but photoelectric effect and Compton effect, these effects or these phenomena could be explained with the particle nature of light or particle nature of photon. Okay, see, there's a light, interference and diffraction can be explained with the wave theory of light. Photoelectric effect, Compton effect, these theories can be explained with the particle theory of light. Okay, or particle nature of light. So in these circumstances, Louis de Broglie in 1924, he proposed that wave called matter wave, that we will discuss in the next class. He proposes that wave called matter wave associated with the particle which is localized with the with the particle. Okay, in 1924, Louis de Broglie he proposed that there is a wave called matter wave. He proposed that there is a wave called matter wave, which is associated with the particle. That matter wave is associated with the particle, which is localized with the particle. There is a wave. Actually, wave is spread in space and particle is localized in space. Louis de Broglie proposes that there is a wave associated with a moving particle. In simple words, we can say Louis de Broglie he proposes that there is a wave associated with a moving particle. And he argued that nature provides symmetry and matter and radiations are two entities of universe. He argued that matter and radiation are the two entities of the universe, and we need particle-like nature and wave-like nature to interpret the experimental results. Okay, we need particle-like nature of the light and wave-like nature of the light for explaining the phenomena. And just before I mentioned, for interference diffraction, wave theory is necessary. Photoelectric and Compton effect, particle nature of photon is necessary. Okay, so Louis de Broglie he proposes that moving body behaves in a certain way as though it has a wave nature. Moving body behaves in a certain ways as though it has a wave nature, which means that wave associated with a moving body. That's simple ways we can say wave associated with a moving body. And Louis de Broglie in 1993 proposed that matter particles should exhibit wave properties just as the light waves exhibited the particle properties. See, Louis de Broglie he proposed that the matter particle should exhibit wave properties just like light waves exhibit particle properties. See, in photoelectric effect, incident one is a light, that's a wave that exhibit the particle property. Louis de Broglie he proposes that matter or particle should exhibit the wave property, just like light waves exhibit the particle property. Is it clear? Louis de Broglie he proposed that the matter particle exhibit the wave nature just like light exhibit the particle nature. Okay. The particle exhibit the wave nature just like wave exhibit the particle nature. Wave exhibit the particle nature means it's a simple example is the photoelectric effect. Instead one is a wave, what we are getting a particle. So which means that the wave exhibit the particle nature. Okay, just like particle exhibit the wave nature. Okay, and these waves are very small wavelengths. In most situations, their presence was difficult to observe. This wavelength is very small, and we can imagine how small it is. Okay, we can imagine. I will tell you. See, de Broglie combined the two equations for photons, E is equal to h nu and E is equal to p into c. We know that E is equal to h nu and E is equal to p into c. That is mc square. E is equal to mc square, that is mc into c. M into c is p, so E is equal to p into c. And then h nu is equal to p into c. We can say from these two equations we can say h nu is equal to p into c. H nu means hc by lambda, that is equal to p into c. Then c get cancelled. Then what we get is lambda is equal to h by p. Okay, so see, lambda is equal to h by p. That is the wavelength associated with the moving particle. Wavelength associated with the moving particle. See, h is of the order of 10 raised to minus 34. It's a Planck's constant. Okay, so since it is very small, h is very small. That's why most of the situations the presence is difficult to observe. For example, there's a bus is moving. As per Louis de Broglie concept, there is a wave associated with that bus. And then can you calculate the wavelength of that wave? Its value is very small, because even we cannot observe, because see, h by p, h is 10 raised to minus 34, p is mass into velocity. Suppose the mass of the bus is around, suppose it's at uh, 2000 or 5000 or 10,000 kilogram for some example. Or 5000, just like 5000 kilogram, its velocity is something is there. See, then lambda is equal to 10 raised to minus 34 divided by again 10 raised to 3 or 4. Okay, 10 raised to 4 is in the denominator. For example, this lambda h is of the order of 10 raised to minus 34. P is again of the order of 10 raised to 5 or 10 raised to 6. 10 raised to 6 is in the denominator. It goes to the numerator. What happens? Its value is very small. And where it is significant, suppose there is an electron. Okay, suppose there is an electron moving with some velocity, then its momentum is mass of an electron is equal to 10 raised to minus 31, 9.1 into 10 raised to minus 31, that range. Mass is 10 raised to minus 31. So see, 10 raised to minus 34 divided by 10 raised to minus 31, what happens is it is significant. So de Broglie wavelength is significant in microscopic realm, not microscopic. Now consider an electron accelerated by a potential of V volt. Then it's suppose there's an electron accelerated by a potential of V volt. Then E into V is equal to half mv square. Its kinetic energy is equal to half mv square. E into V. Suppose the accelerated by a potential of V volt, then its energy. Suppose there is an electron accelerated by a potential of V volt, then its energy is equal to small e into capital V. Charge of the electron into potential, which is equal to half mv square. It's kinetic energy. Okay. Then we can say we know that P is equal to m into V. Then we can say, see, this is equal to P square by 2m. The kinetic energy can be denoted as P square by 2m. Okay, we can multiply with the m here and divide by m. So m square v square divided by 2m. That is half mv square itself. We can write in paper half mv square, then multiply by m and divide by m. So m square v square by 2m. M square v square is equal to p square itself. Okay, so we can write p square is equal to 2me into v, or p is equal to square root of 2me. Now coming to the de Broglie wavelength, lambda is equal to h by p, or lambda is equal to h by square root of 2mev. So instead of this p, you just write square root of 2mev. That is the wavelength of an electron accelerated by a potential of v volt. Okay. So de Broglie also receives Nobel Prize for. Okay. So today we discuss about the Planck hypothesis. He receives Nobel Prize. Photoelectric effect, another Nobel Prize. Compton effect, another Nobel Prize. Louis de Broglie concept, dual nature of matter, another Nobel Prize. And next one is Davisson Germer experiment. It's an experiment which confirms the de Broglie waves. It's an experiment which confirms the de Broglie wave. Actually, this experiment is not the Davisson Germer experiment only. It's an experiment of Davisson Germer Thomson experiment. That Thomson is G.P. Thomson. G.P. Thomson is the son of J.J. Thomson. Okay, so this experiment is Davisson Germer Thomson experiment. That Thomson's experiment is Thomson is no one other than G.P. Thomson. G.P. Thomson is the son of J.J. Thomson. I think you may have heard about J.J. Thomson. J.J. Thomson, who discovered electron, and he says that electron is a particle. And his son G.P. Thomson, he proves that electron is a wave. Okay. So J.J. Thomson receives Nobel Prize for his contribution in electron, which is as a particle, and G.P. Thomson, he also shares in the Nobel Prize for proposing that electron is a wave. Okay, father proposed that electron is a particle, he receives Nobel Prize. Son proposes electron is a wave, he also receives Nobel Prize. Okay, now we are moving to the experimental part of this Davisson Germer experiment. Okay, we can see there is a filament and there is a supply. Okay, there is a supply and there is a filament. So what happens is this filament get heated. Due to this supply, there is a flow of current. So this filament get heated. So due to this thermionic emission, there is a lot of electrons ejected from this filament. There is a supply voltage. There is a filament. Due to thermionic emission, there are a lot of ejection of electrons from this from this filament. And these electrons are accelerated by a potential of V volt. See, you can find in this figure there's a voltage V. It's accelerated by a potential of V volt, which means that the ejected electrons highly accelerated with this accelerating voltage. And this highly accelerated beam of electrons is collimated. There is a collimator, which means that what happens to, or the main duty of this collimator is to make a narrow beam of electrons. Initially there are a lot of electrons, then it is highly accelerated, which means that electrons gets more energy, and this uh, highly energized electron beam is passes through a slit or collimator. What happens is we are getting a narrow beam of electron. This narrow beam of electron, see, look at this figure, falls on the nickel target or nickel crystal. After scattering, see, it's a nickel crystal. It's a nickel crystal. What is crystal? It's a periodic arrangement of atoms or group of atoms. It's called crystal. It's a periodic arrangement. Okay. So in one plane there's a periodic arrangement of atom, another plane periodic arrangement of atom, another plane periodic arrangement of atom. We can say in 3 dimensions it's a periodic arrangement. So one plane, another plane, another plane, another plane, just like. So periodic arrangement of atoms or group of atoms. There's a nickel crystal. After scattering, there's a detector called mobile electron detector. This detector will detect what happens to this electron, or yes, what happens to this electron. This mobile detector that detects this scattered electron, just like this scattered electron. And this whole apparatus is kept in an evacuated chamber. This is a glass evacuated chamber. There's a filament, there is a supply voltage. So due to thermonic emission, there is a lot of electrons. These electrons are highly accelerated by an accelerating voltage. After that, it passes through a collimator or slit. A narrow beam of light is falls on the nickel crystal, and there is a mobile detector or electron detector that detects. That's actually the construction or the experimental part of this Davisson Germer experiment. Okay. In this, now we are moving to actually what happens, or what happens in this Davisson Germer experiment. If particle has a wave nature, then it under appropriate condition they should exhibit diffraction. See, there's one very important thing. If particle exhibit wave nature, as per de Broglie concept, what's de Broglie concept? Dual nature of matter. Particle possess wave nature. If particle possess wave nature, then it should exhibit wave phenomenon. Wave phenomenon means interference or diffraction, etc. Okay, so as per de Broglie concept, particle exhibit wave nature. If particle exhibit wave nature, it should exhibit wave properties like diffraction or interference, etc. Actually, this is the essence of this Davisson Germer experiment. Now we are moving to electrons were directed into nickel crystal. See, in this case, electrons were directed to nickel crystal, and accelerating voltage is used to control the electron energy. See, there is an accelerating voltage. These electrons are directed towards nickel crystal. There is an accelerating voltage. The voltage is used to control the electron energy. Initially, due to thermonic emission, this electron may possess very low energy. After acceleration, it gets higher energy that is directed towards this nickel crystal. Okay, so this after scattering, these electrons are detected using a mobile detector. Okay, so see in this figure, there's a filament, accelerating electrode, there's a small slit. After that is nickel crystal scattered off. There's a mobile detector. Okay, see in classical physics, which predicts that the scattered electrons will emerge in all directions. As per the classical theory, after scattering by this nickel crystal, it emerges in all direction. It emerges in all direction, which means that there should be a uniform intensity in all direction. There should be an uniform intensity in all direction. That is classical expectation. So the classical physics predicts that the scattered electrons will emerge in all directions. Instead of continuous variation of scattered intensity with an angle, distinct maxima and minima were observed. See, after scattering, we are expecting a uniform intensity. But instead of getting uniform intensity, some point maximum intensity, then minima, then maxima and minima. This type of intensity distribution is observed. Is it clear? After scattering of electron by nickel crystal, the classical expectation is we are getting a uniform intensity. But instead of getting uniform intensity, we are at a particular angle, detector angle at a particular angle and a particular voltage. That I will tell you the significance of that particular voltage. For a particular voltage, there is a intensity maximum. After that, intensity minimum, then intensity maximum, intensity minimum. This is just like a diffraction pattern. Diffraction pattern is similar to X-rays would observe if electron behaves as a wave. So this is just like a diffraction pattern, which means that this is a diffraction pattern, which means that electron should behaves like a wave, because diffraction pattern is a result of wave property. Diffraction pattern or diffraction is a result of wave property of light. So the wave property of light is demonstrated. Okay, after scattering, there is a mobile detector. If we place a mobile detector at a particular angle which is 50 degree and the accelerating voltage is 54 volt, please listen. There is a mobile detector. See, there is a mobile detector. Suppose the mobile detector is placed at an angle of 50 degree from this normal 50 degree, and this accelerating voltage is of 54 volt, then we are getting a high intensity P. Just like 54 volt, we are getting a maximum intensity. Some other voltage there is a maximum intensity, but at a particular voltage 54 volt, which gives the maximum intensity. Otherwise we will get some intensity. This pattern is maximum at a 54 volt and 50 degree. I will tell you the significance of this 54 volt. The distinct maxima and minima is due to the constructive and destructive interference of electron waves scattered in this direction from the crystal. So this type of graph, maxima and minima, this is due to the interference of electrons scattered from the nickel crystal. This maxima, minima, this is due to the interference of electron waves scattered in this direction from the crystal. Okay, now we are moving to the significance of this 54 voltage. See, it is found that the wavelength of electron wave calculated using the de Broglie wave equation, lambda is equal to h by p. So de Broglie wave or wavelength associated with an electron can be calculated using lambda is equal to h by p, and that obtained using the Bragg's equation 2d sin lambda is equal to 2d sin theta is equal to m lambda. That's a Bragg equation. Okay, so Bragg equation which is equal to 2d sin theta is equal to n lambda. So for obtaining the Bragg diffraction, 2d sin theta is equal to m lambda, which means that, please listen carefully, 2d sin theta is equal to m lambda, which means that there should be a relation between lambda and d. This Bragg diffraction, listen, the Bragg diffraction observed when this lambda is of the order of d or d is of the order of lambda, then only this Bragg diffraction occurs. Okay, now I would like to tell you, see, for an electron accelerated to a voltage of V volt, then its wavelength is equal to lambda is equal to h divided by square root of 2 MeV. Lambda is equal to h divided by square root of 2 MeV. For a particular voltage of voltage of V, for a particular voltage, that is for 54 volt, this lambda matches with this Bragg's equation. Is it clear? For de Broglie wavelength, lambda is equal to, suppose there is an electron is accelerated by a potential of V volt, then that electron wavelength lambda can be calculated using lambda is equal to h by square root of 2 MeV. Then we will get lambda. Okay, some other voltage there is a lambda. For 50 voltage there is lambda, 50 volt, 60 voltage there is lambda. For 54 voltage there is lambda. That particular voltage 54 voltage, there is lambda. That lambda matches with this equation 2d sin theta is equal to m lambda. Okay, so for Bragg diffraction, once again I would like to tell you, for Bragg diffraction, or the Bragg equation is 2d sin theta is equal to n lambda. This works when this small d is of the order of lambda. Okay, and this lambda and this d is of the same order. And for particular voltage 54 voltage, this lambda, de Broglie wave lambda, matches with this equation, and that is significance of this 54 volt. Is it clear? For that particular 54 voltage, lambda is equal to h by square root of 2 MeV. We will get 1 lambda. That lambda matches with this 2d sin theta. For 50 volt or 60 voltage, it does not that much match. Okay, so 50 voltage it's somewhat matching, but we are getting another intensity, but maximum intensity observed for 54 volt. So this shows that beam of electrons behaves like an X-rays, undergoes diffraction at a reflecting crystal surface, and thus exhibit wave-like property. See, in Davisson Germer experiment, incident one is an electron, what we are getting is a diffraction pattern. Diffraction pattern is a result of wave nature. So in photoelectric effect, incident one is a wave, what we are getting is a particle. In Davisson Germer experiment, incident one is an electron, what we are getting is a wave. Okay, so photoelectric effect demonstrate the particle nature of wave. Davisson Germer experiment demonstrate the wave nature of particle. Okay, that's about the Davisson Germer experiment. So thank you very much. Next we will discuss about wave function, something like. Okay, thank you.